Hello, this video covers the questions that are asked in the U5 Module 3b homework. So we're going to start, we're given a mechanism and we're asked to find the rate law. So this is really coming from the last homework, Unit 5 Module 3a, where we need to assign from the slow step, the rate law. All right, so we do that by first identifying the reactants that are in the rate law, A and 2B. We use our rules that we used for the equilibrium constant, which is we multiply the concentrations, and if there's a coefficient, we use the power. So the 2 we put there comes from the 2 in front of B in the slow step, so we multiply the concentrations and we square B. So the slow step answer is C. A is incorrect. That is the overall reactions rate law from the using the overall reaction for the rate law, which is incorrect. You must use the slow step, elementary step. All right, another question, very similar in terms of we have a slow fast. We're asked to identify which graph best represents it. So again, always the first step is to identify what the rate law is, which is Ka times B. Here the coefficient is 1 for each. And now what we're going to do is we're going to graph rate versus the concentration of A. And remember, we do that assuming concentration of B is constant. We do not include it. So if we do that, it's really rate. So we have our constants here. Rate equals some constant times the concentration of A. When we make the plot, we call the constant part M, and we're plotting X as the concentration of A. This is a line, first order kinetics, straight line with the slope is a constant. Right here you're given the rate law, and now we want to know what is the new rate if you change A and you change B. All right, so what we do here is we form a ratio, rate new over rate old, and then we put in for the rate new the factors that are now being changed. So we see that, okay, A is being cut in half, right? The initial concentration of A, so that's where we put A0, is cut in half, and the initial concentration of B is now tripled. So we do that and we include the powers. Now our old rate are just the initial concentrations of A0 and B0. Right, B0 squared. All right, so why do we do it that way? We do it that way because a bunch of values are going to cancel. We're only going to be left with the factors raised to the powers from the rate law. So we have 1/2, which was raised to the first power. We have 3, it was tripled, 3 raised to the square. And that's because now we have B0 here squared, so that cancels. We now have A0, that cancels. And since we didn't change temperature, K's cancel. And that gives us 9/2. All right, so now the rate new, which is what we've been asked to calculate, over rate old, well, the rate old was given to us as 0.13 molar per second. So we can now solve for rate new, and it's 0.0585 moles per second, which is C. Okay, so anytime you're asked to analyze an equation in which you are changing concentrations in this way, ratios are very useful. Okay, we have another slow-fast mechanism, but this time we're asked to calculate the rate constant K. So we're given the rate law. So the slow step, we have to construct the rate law. So the rate law is coming from the slow step as A times B squared, just like our first problem we worked on. We can now solve for K as rate divided by concentration of A times B squared. And now we're given these three variables. We're given the rate as 0.1 molar per second. We're given A, and we're given B. We Put these values into our calculator, and we see that we get 5,000 meters seconds molar to the -2, seconds to the -1, and that will give us the units. The units weren't asked for here, but we would get them that way. The molars cancel, there's a 2 there, and we have the seconds. All right, in this problem, we are given a 2-step mechanism. Now, it's always nice to put what the steps of the mechanism are. So let's just write here, we have 1, we have NO2 breaking up into NO plus O. And then we have O2 reacting plus O to make O3. Right, so those are our 2 steps. This is happening slow, this is happening fast. And we add it together and we get NO2 plus O2 making NO plus O3. Right, so those would be our overall reaction here. Okay, so the problem though asks how many times faster is this reaction? Okay, so whoops, sorry. Okay, so we have our individual steps here, slow, fast, and our first activation energy, the forward activation energy, the activation energy of the slow step is 306.5. That's the forward activation energy. So when we want to look at how many times faster a reaction is when we change temperature, that is going to be the ratio of rate constants in Kelvin. So we're saying we go from 100 degrees to 200 degrees, so 473 to 373. And the equation we have is e to the minus activation energy over R. Whoops, I did it again. Times the reciprocal temperatures. Now keep in mind this formula is KT2 over KT1, which is e to the minus activation energy over R times 1 over T2 minus 1 over T1, right? So that's our formula. And that's what we're putting here. We have our forward activation energy. We have R in kilojoules per mole. Here's our T2, and here's our T1. You can think of T2 as T final, and T1 as T initial. All right, so when we put these numbers together, remember if we're going to put these numbers in our calculator, it would look like this. 473 x minus 1 minus 373 x minus 1 equals, right? And then we would multiply by our activation energy times the 306.5 equals, and then the answer divided by minus 8.314, E key minus 3. And if you do that, you should get plus 20.895. And when you put that in your calculator, we see that the reaction increases 1 billion times. 1 times 10 to the 9th is how much faster the reaction is. So you want to make sure you practice this calculation. And using the reciprocal keys is one of the ways in which you can avoid common mistakes with parentheses. All right, this question is about determining the rate constant at a new temperature. Okay, so let's do that. The first thing now, like the problem we just did, the factor faster would be the higher temperature over the lower temperature, right? That's the how many times faster is a reaction at 298 versus 150. But what we have here is what is the factor of the reaction slowing down? The slower reaction at colder temperatures, at lower temperatures. So this is the how many times slower is the reaction. And that just uses the same formula. We put in our activation energy, we put in R, and now the temperature, right, our final temperature is 150, and our initial temperature is 298. All right, so if we do that, what we'll find is now this ratio, the how many times slower is the reaction, is e to the minus 17.6. If we put e to the minus 17.6 in our calculator, we get 2.3 times 10 to the minus 8. So this is a big reduction in the speed of the reaction. And we're asked to calculate numerically what K150 is, which is our K298 times how many times slower this reaction is. So if K298 is 2.3 times 10 to the third, we multiply by the factor it is slower to 2.3 times 10 to the minus 8. And if we do that, we get K298 equals 5.2 times 10 to the minus 5. This is molar minus 1, second minus 1. It's in the same units. It's just slower. So you want to practice doing these calculations, making sure that you can identify which constant is on top, right? It's always K is T final over K T initial, right? So whatever, just make sure that the given information that you use reflects that, because T final and T initial are going to go into the equation that way. All right, these are all the problems that students have asked questions about in office hours regarding this homework assignment. And keep in mind that we will also have a video on worked out problems from exam 2A.